Greetings to all. Our project Atmox AI cloud-based prediction and detection using machine learning algorithm guided by Andosa. Moving on to content page, these are the contents which we are going to discuss in the upcoming slides. Next, introduction. Our project utilizes data science and artificial intelligence to monitor meteorological variables aiming to mitigate human suffering caused by cloudbursts. From 2018 Cloudburst, the project aims to improve disaster preparedness through accurate cloud-based predictions. Atmox AI employs MATLAB for data processing and feature selection, enabling the researchers to identify crucial indicators of cloudburst. Next, the objectives. We have mainly have four objectives include to develop a self-powered autonomous intelligence system to predict cloudbursts and alert people in vulnerable areas, to monitor and analyze atmospheric parameters using embedded system and AI to improve safety of people in landslide-prone areas. Next, to predict cloudbursts and high-density rainfall so people can move to safer locations before the occurrence of landslide. Next, to alert rescue forces and authorities. Next, mission statement. Our mission is to improve disaster preparedness and mitigation in challenging environments like hilly regions and remote villages by developing a resilient and cost-effective cloud-based prediction system using advanced sensor technology and strong GSM communication modules, as well as state-of-the-art of machine learning algorithm. Our product provides accurate and timely warnings to vulnerable communities facing extreme weather conditions. Next, literature review. We have taken reference from almost 7 standard papers, and the literature review is given in the following pages. Next, we have a wide variety of applications ranging from agriculture, energy, disaster management, transport, urban planning, and healthcare. Next, our target users, they vary from local residents and communities, NGOs, education and research institutions, environmental conservation and water source management, meteorological and climate scientists, local government and disaster management authorities. Yes, these are our target requirement, varying from real-time monitoring of environment parameters, real-time processing of data, real-time data processing, robust communication, easy repairability, easy implementation, consumes less power, self-sustaining device, etc. Next, this is our need metric, and the needs of our device are mentioned in the following table. Next, this is our design specification. We have designed our product based on this design specification, as well as considering the need metrics and the and this is our work plan, and we have completed our project based on this work plan. Yes, this is our block diagram. This block diagram, we mainly have four different sensors, namely DHT11 for temperature and humidity sensing, PMP 180 for pressure sensing, rainfall sensor for detecting the intensity of rainfall, and soil moisture sensor to detect the soil moisture. And these different sensors send the data to ESP32, and the ESP32 is the main processor here. And from ESP32, the data is sent to Google Spreadsheet and Blink, and the user can visible with the data from Google Spreadsheet and also from Blink platform. Uh, the ESP32 is taking a power of 5 volt, and we have used a 12 watt solar panel to charge a rechargeable 12 volt battery. Yes, this is our circuit diagram. The different sensors are connected to different pins, and the data from the pins are sent to cloud using ESP32. Yes, this is our power reduction circuit. In this, um, by using this circuit, we convert a 12 volt power to a 5 volt. In this, we use a voltage regulator, namely LM7805, and we have two diodes, IN4001, and we use that diodes to stop reverse polarization of current, and two capacitors, namely C1 and C3 of 2200 mF and 0.1 mF. They are used for stabilizing the voltage in the input and output. And we can also use another of 1000 and a 450. And we have used an LED as a status indicator and a 1K resistor for its protection. Next, we have process flow. So the basic working of a project is such that the main purpose is we have a system which consists of different sensors for collecting different environmental parameters, and that data is sent to a Blink IoT platform and a Google spreadsheet. From that data, from that we create a data set, and the data set is sent to a machine learning platform. From machine learning platform, we carry out ML, and after ML we can predict cloud bus, and from that prediction we will be given to alert system and we can alert the community. Next, we have a use case diagram. As I already mentioned, our main purpose is to collect data from different sensors. So there's a sensor data collector who collect different data, namely temperature, pressure, humidity, rainfall, and soil moisture, and all that data can will be stored as a data set, and that data set is sent to a MATLAB, and a simulator uses MATLAB to perform machine learning algorithm to provide alert to the user. Next, sequence diagram. In this sequence diagram, we have clearly explained how the data from each sensor is sending and how our system works. Next, this is our PCB design, and we have designed our system based on this PCB. This is our PCB implementation. Next, the requirements. We have used different softwares, namely Arduino IDE for program, Blink, ECDA, MS Office, and hardware include ESP32 Node MCU, DHT11, rain density sensor, PMP180, and soil moisture sensor. First, ESP32 node MCU. The ESP30 node MCU operates with a voltage range of 3.3 volt to 5 volt, and it typically consumes around 200 milliampere of current in active mode. Its basic working involves executing user programmable code, connecting to Wi-Fi and Bluetooth network, and interfacing with various sensors and actuators while adhering to their electrical parameters. Next, DHT11. I typically operate within a voltage range of 3.3 volt to 5 volt. Basic working involves sensing the ambient temperature and humidity, converting this measurement into digital signal, and transferring data over a single wire communication protocol. Next, we have soil moisture sensor. This moisture sensor also works in the range of 3.3 volt to 5 volt. And sensor's basic working principle involves measuring the electrical resistance between the probes inside into soil, which changes based on the soil moisture level. Next, BMP180 is a digital barometric pressure and temperature sensors developed by Bosch. The sensor has a high resolution measuring pressure with up to 0.01 Henry Pascal resolution and a temperature with 0.1 degree resolution. It operates in a pressure range from 300 Henry Pascal to 1100 Henry Pascal. Next, bill of materials. These are the bill of materials, and we have a total cost of 3,645 rupees for our project. Next, moving on to results, we were able to integrate four different sensors, namely DHT11, BMP180, soil moisture and sensor, and in real time, the data from the sensors are visible to user using a Blink platform, and this is a Blink console. Next, the data from the sensors will be real-timely stored in a Google spreadsheet, and we have developed a prototype, and we have set up that prototype in our college premises for almost 6 days, from 18th of April to 24th of April, and we have collected about 7,500 data of different sensors: temperature, pressure, humidity, soil moisture, and rain intensity. And we have made that into a data set, and we have performed MATLAB on that particular data set. The data from the sensors will be updated in every 1 minute. So this is a MATLAB plot for the data which we collected in the different dates, and we can see a clear variation from this graph. Next, we have plotted temperature versus pressure at the time of rainfall and temperature versus humidity at the time of rainfall. So by close observation and analysis, we identify that when there is a huge rainfall, the value of rain intensity sensor and soil moisture sensor far below 1000. So we set 1000 as a threshold, and when a particularly when the value become lower, that we set 1000 as a threshold, and we have identified high intensity of rainfall the time when it fall below the value 1000. Next, we have plotted a correlation of temperature, pressure, and humidity, and the region showing denser region is the region where temperature, pressure, and humidity correlate at the time of rainfall. From the graph, we identify that humidity is between 70 and 75. Pressure is between 1.007 and 1.008, and temperature is between 29 and 31. Next, the data set, we use that particular data set in ML, and we have performed three different tests to identify the best feature. First, we have performed case test. In case test, we have chi-square value h and probability value p, such that if the chi-square value h is closer to 1 and the probability value p is closer to 0, then it is a good feature. And from our test, we identify that temperature and humidity was the best two features. Next, we have carried out test to plot histogram of our data set. And from that, we identified that temperature and humidity was better. It can be identified that here the red line indicate the significant change in the rain density, the green line indicate no significant change in the rain density. So if at a particular temperature, if 2 point coincide, then it indicate that the two features are not easily distinguishable there, so that less number of coincidence shows more good feature. Yes, we have also carried out performance parameter tests in which we find out sensitivity, specificity, AROC, accuracy, PPV, and NPV value. PPV means positive predictive value, and NPV means negative predictive value. And from that, we identify that temperature and humidity are best value. The sensitivity, accuracy, and PPV value must be closer to 100, and NPV must be closer to 0. Next, we have carried out machine learning technique. First, we have trained our data set. There are different. We have chosen binary classifier as our machine learning technique, and in binary classifier we get maximum accuracy for decision tree. So we have carried out our test in decision tree. So we have plotted. This is a scatter plot for fine tree, median tree, and coarse tree. In this red dot, orange dot indicate significant change in the rain density, and blue dots indicate non-significant change in the rain density. We also plotted ROC validation curve for the data set, and in that we can identify AUC value. If AUC value is closer to 0, then we can identify that it is the best feature. Then we have also find out the confusion metrics for our dataset. In the confusion metrics for the dataset of non-significant rain change, 98 was predicted correct and 1 was only predicted wrong. And in significant rain change, 94 was predicted correct and 5 was predicted wrong. We have also tested our particular data set using machine learning algorithm, and we have plotted scatter plot, ROC validation curve, and confusion matrix. And this is our performance indicators of decision. And the training accuracy and testing accuracy is almost same for different trees. And by prediction speed and training time, we identify that coarse tree is the best among the three different trees. This is our product design we developed using uh, Blender. Yes, this was our prototype which we set up for data collection. This is our final product. So in conclusion, our cloud-based prediction system using different sensors, data processing and feature selection has a potential to be a valuable tool for saving lives of property. This early warning system can then be used to alert people in vulnerable areas so that they can take necessary precautions such as evacuate to safer place. This is our future scope. We can integrate satellite imagery and other data, develop mobile apps for public warnings, continuous model improvement with new data, develop cloud-based mitigation strategies, explore hybrid approaches. And these are some of our achievements. And these are the references which we have taken. Thank you all.